Dimensional analysis is a tool that we're going to use to tell if an equation is just reasonable. And scientists often do this, that they'll think they know a relationship and they can just look at the dimensions of the variables within that mathematical relationship. And if those variables don't match up, then they know that that relationship's not true. So it's a useful thing to do. It's also useful just for you to flex your algebra skills just a little bit. We're not going to have a whole lot of math in this course, but I like to do this right up front so that students just remember how to do basic algebra. So when we look at an equation, we can treat the units algebraically. That is, we'll take each variable and replace it by its units, and then we'll cancel out variables when they cancel, and we'll add them up when they add. And we're really looking for an equation so that all the units match up correctly. First, let me just give you some common dimensions and units. You probably know these, but area is length times width, and that's in units of meters squared. Volume is length times width times height, and that's in units of meters cubed, or cubic meters. A velocity or speed is a distance divided by a time, and that's going to be in units of meters per second. And then acceleration is a velocity per time. So how does the velocity change as a function of time? And this is meters per second, right? Meters per second is velocity. How does that change with every second? And then we usually just write this as meters per second squared. So let's just do some examples. Are these equations dimensionally correct? Well, here we have x, and we know that x is a distance, and it's going to be in units of meters. Velocity is in meters per second. And then time is in seconds. And sometimes I like to do these as seconds over 1. Or you might have seen people in the past, if you had a high school teacher, that might have set up a ladder like this, where I had meters per second, and then seconds. And then you could cancel out the units as they come along. So here I know that those seconds, they're going to divide because seconds over seconds is equal to 1. And then that'll just leave units of meters on the right-hand side. So I have units of meters on the left-hand side and units of meters on the right-hand side. So I know that that equation is dimensionally correct. In this second equation, we have a couple complications. We have these terms. These, x naught, is you can think of as shorthand for x at t equals 0. That's what the naught is, like NAUGHT, x naught, or x at the t equals 0. Or sometimes we'll write this, by the way, with an I for x initial. This is your initial condition, and we'll use this throughout the course to denote an initial condition. What is the value of that measurement at the very first time? As far as units are concerned, that doesn't change the units. So here I'm going to have units of meters. Here I will also have units of meters. V naught, that's just your initial velocity, is going to be meters per second. And then t is also going to be in seconds. I'm going to do it as seconds over 1, just so I recognize that that seconds is in the numerator. Here, when I have a coefficient like this, most of the time, this coefficient will not have any units. At least as far as we're concerned, it won't have any units. This is usually a byproduct of some function in calculus that you've done, some action that you've done in taking derivatives or integrals. And so I'll just forget about it and not have any units at all. I know acceleration is meters per second squared, and then I have time squared, which is in the numerator, so it's second squared over 1. Now I can get rid of some of these. I know those cancel and those cancel, so leaving 1. Seconds over seconds is 1. Second squared over seconds is 1. And then I'm left with meters, 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 and meters. So all of those are correct. And then finally here, this is a little bit more complicated. I have V is meters per second. A, I'm going to write this a little bit differently. I'm going to write it as A and then 1 over T. Just separate those two variables and recognize that the time is in the denominator. So I'll write it a little bit differently. So A is meters per second squared. And then T is 1 over seconds. Now already you can see that I'm going to have a seconds cubed in the denominator, and so that will not be the same units as what I had for the V. Plus Get rid of the half there. It's just an integration constant, we call it. And this is meters times time, which is seconds. So none of these are the same. I have meters per second here, meters per second cubed, and meters second. So this one is not dimensionally correct. Let's consider an equation. Like, let's say that I have x equals 3s divided by m. And I want to know what are the units of s. So these are all variables. I want to know what are the units of s. And I'm going to tell you that x is meters and m is in kilograms. All right, I'll get rid of the 3. That's just sort of doesn't have any units. If I want to know the units of s, then s, solving this equation for s, you can think of it as cross multiplying or multiplying both sides by m. S is equal to x times m. X has units of meters. Be careful because now I'm switching from the variables to the units. And so the variable m actually has units of kilograms. Don't worry, I know these are a little foreign to you right now. It's probably been a long time since you've seen these, but as we move through the course, they'll become more familiar to you. So then the units for S are going to be meter kilograms. You have a similar question down here in the quick test questions.